This program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest UCTV programs.
Good afternoon. My name is Rod Elfernus, and I'm Dean of Engineering here at UCSB. And on behalf of the entire College of Engineering community, the faculty, the students, and the staff, I'd like to welcome you to this celebration to honor Professor Tsuji Nakamura receiving the 2014 Nobel Prize in Physics. Thank you very much for joining us to share in the excitement and the campus pride that this, the 6th Nobel Prize for UCSB faculty, brings to this campus, and to honor Tsuji for the great work that he has done. I'd like to make a very special welcome to those of you who are coming from off campus. Tsuji Nakamura is professor with joint appointments in Materials Department and the Electrical and Computer Engineering Department within the College of Engineering here at UCSB. He's also co-director of the Solid State Lighting and Energy Electronics Center, for which he also was one of the founding directors. The Nobel Prize in Physics for 2014 was awarded jointly to Tsuji, to Osamu Asaki, and Hiroshi Amano for the invention of the efficient blue light-emitting diodes, which has enabled bright and energy-saving white light sources. I believe that the Nobel Committee has captured well the discovery, as well as very, very importantly, the huge impact of this very important work on humankind. We in the college are extremely proud of Tsuji and the great work that he has done in discovering the power of the semiconductor material gallium nitride to produce blue light when current is passed through it. You can imagine the excitement and sense of pride on campus the morning that we heard the great news. We enjoyed a very, very wonderful toast. We are also very proud of the work that Tsuji, in collaboration with colleagues on campus, have done over the last 15 years to move from the discovery of possibility of LED to the commercial viability and availability of LED lights that you can now find at Costco in big abundance. And that when fully deployed, when LED lighting is fully deployed, will substantially reduce the electrical power required for global lighting. That spirit of collaboration, as well as the entrepreneurial spirit that drives our faculty here at UCSB to applications that positively impact people's lives, so evident in this story of gallium nitride and LED lighting, is in fact a hallmark of our campus more broadly and a huge advantage for all of us. A few words about today's program, which is intended to be both informal and also celebratory. The centerpiece, of course, is Tsuji's lecture. Prior to Tsuji's lecture, we've asked Tsuji's close colleague and co-director of the center, Steve Denbars, who is also a member of the materials as well as the electrical and computer engineering departments, to provide his insight, the story on the impact of Tsuji's early work, discovery, and on the recruitment of Tsuji to campus, as well as to speak to the huge impact of solid-state lighting and power electronics that this technology has made possible. Then Nobel laureate Herb Kromer will offer his insights of Tsuji's work and its scientific and practical impact. Interesting, Herb's work on double heterostructures, for which he received the Nobel Prize in Physics in the year 2000, has been an important element in Tsuji's work. Before asking Steve to come to the podium, a couple of announcements. First, I want to thank Teresa Pollock, Chair of the Materials Department, and Joao Hispania, Chair of the Electrical and Computer Engineering Department, for their help in organizing this event. A very special thank you to the staff of the College of Engineering, who have worked very hard at very short notice to pull this off, and a special thank to Britta for all her work. And now, if you will please mute your cell phones. And I'd just point out that following Suji's lecture, there will be plenty of time for questions, and then following that question session, we will invite you to join us on the patio for a reception. Again, we are all delighted to have you join us for this celebration. Steve.
Thanks, Rod. I'm Steve Denbars. I'm co-director of the Solid State Lighting and Energy Electronics Center, along with Suji. He's been a close colleague here since 2000. And I was asked to talk a little bit about the background story of Suji and recruiting him, and kind of even how I met him and then got him here to this campus. But then I'll talk a little bit about the impact. So just a couple minutes, but give you a little bit of a flavor for what it was like back in 1993. When I'm working on red LEDs, this was my specialty. We only had the color red and a very dim green, and you'd only see these LEDs for the red circle in the traffic signal or the tail light in your car and maybe in a calculator. So the field was very small, maybe fewer than about a few thousand workers worldwide in it. And I was doing a sabbatical in Japan, and I went to a conference about this size in Japan, and Suji came and he gave a lecture in which he showed these blinding blue lights. They're much brighter nowadays than the white, but it was pretty bright. And after the lecture, nobody went up to congratulate him. And there's been this huge breakthrough because Japanese people are a little shy. So me not being shy, I went up to him immediately with my business card and gave it to him. And nobody was taking him into coffee. So we sat down and started talking. But he was very modest and open. And I told him it was a great, result. Subsequently, many people jumped into this field. At the time, there was only 3 researchers working on the material that he got this blue light with, which then led to this white LED revolution. Within a span of about 3 years, the number had jumped from 3 people to about 3,000, and today there's over 100,000 people employed in this industry. So that's kind of amazing to see from a very small group of people that you can build something very big. Anyway, so that's 1993. You go forward 7 years. He's still the leading researcher. 7 years later, his company had moved from nowhere in LEDs to the #1 LED company, over $1 billion in sales in a fairly short time span. And I saw him again at a conference, and he says, "You know what? What do you think about UCLA? I just got this job offer from UCLA." And I just about fell out of my seat because I didn't ever think he'd want to leave Japan, and let alone become a professor. So I said, well, UCSB is much better than UCLA. Moreover, he had some colleagues that were, my colleagues were also his friends, Professor Umesh Mishra, who's sitting here in the second row, and Jim Speck. And I said, look, if you come to UCSB, you'll have a good team to work with. And in the end, he got 10 offers from not only companies, but from Stanford and MIT, and UCSB built him out because I think what Rod said is true. We have a very collegial atmosphere here, and we were able to offer him a welcome family, research family to come into. So that was the story of his recruitment and why we beat out all these other great universities. But the story doesn't end there, obviously. Since coming to UCSB, Suji has built up the largest academic center in the world, along with our colleagues. The uses for this material, this LED, has spanned from just a simple light bulb. Flashlight was the big thing driving it first, to LED TV. So when you go to Costco now, you see these big LED TVs. That's all backlit with these LEDs, white LED Inventions. Then there's the light bulb, obviously, that we're seeing now, widely deployed, traffic signals. And then, of course, everybody has a smartphone in their pocket. Well, it turns out all the lighting in your smartphone, unless you have a Samsung, is gallium nitride LEDs. However, if you have a Samsung, it's organic LEDs, which is another Nobel Prize winners here at Invention. So we'll talk about that another time, hopefully. So that's what it's spanning now, but it's even more broad than that. So gallium nitride, this material that only these 3 people were working with, and Suji finally took it and enabled this revolutionary product, is now affecting many other industries. My colleague, Professor Mishra, has subsequently spun out a company that's doing power electronics, and there's now, I think, 20 companies working on the field of power electronics. That's not switching light, but what it's doing is it's switching energy, particularly alternating current to direct current electricity, more efficiently than what you could do with silicon. That has the potential to save as much energy as LED lighting. Speaking of energy savings, just in the United States alone, the Department of Energy estimates that in the next 15 years, we will save $98 billion in electricity just due to those LED light bulbs you see over there. That's just the United States. And that's the equivalent of 50 power plants in the United States in 15 years from this invention. So this is a really big energy savings, and that's what the Nobel Committee realized. Again, he just keeps plowing ahead. He's filed 150 patents since coming to UCSB. He's working on the next greatest thing, we think, which is laser lighting. But more importantly, he's helped educate and graduate over 50 PhD students. And like I said, from just a few researchers, it's now hundreds, 1,000 people working in this field. So I'm real proud to have witnessed this huge success in the field of material science and electrical engineering. So I guess I got to thank Suji for my job, so thanks.
And now some words from Nobel laureate Herb Kromer.
Ron doesn't have the foggiest idea what I will be talking about. Although we are celebrating today, I think many of you know that the actual award takes place on December 10th. In fact, it always takes place on December 10th, because this is the anniversary of the death of Alfred Nobel. He died almost 120 years ago in 1896. And when the executors of his will opened the will, they found to their surprise that he had dedicated most of his fortune to be turned over to a foundation, and that the income from that foundation should be used to support 3 annual prizes. One of the prizes was in physics, and the Nobel's own specifications for this prize were very simple: to the person who has made the most important contribution to innovation I'm sorry about this. To concepts and invention. And of course, the question is, with a specification like this, who is going to make the choice? And Nobel specified this one. Yeah, let the Royal Swedish Academy of Science select both the winner for the physics and for the chemistry prize. And that was to the great surprise of the Royal Academy, because they had never heard about this one. But they eventually agreed, and so they apportioned the role to one of their classes, to the so-called physics class. The Royal Academy consists of 10 classes. Physics is one of them, chemistry, engineering, and there's a total of 10. And so the physics class was given the job to pick the winner in the physics field. Now, of course, these were all professors at physics at various Swedish universities. And so it is very clear that there was, right from the outset, a very, very emphasis on research, discovery. That's the word I missed: discovery and invention. And so this then persisted throughout most of the 20th century. And if you look at the various Nobel Prizes through the 20th century, almost all of them deal with discoveries. There are a few inventions, but most of them are inventions of scientific instrumentations. In other words, they were not part of society at large. They were part of the research community. There was one important exception, and that was the 1909 Nobel Prize to Marconi for invention and development of wireless telegraphy. And if you think about this one, this was a huge change. It suddenly changed the entire communications procedures throughout the world. You could suddenly get a message from Europe to America, or from America to Japan, or the other way around, within a fraction of a second, rather than having to put it on paper and sending it by a boat, which took at least a week and probably 2. And so this is an important idea here, that invention qualifies for a Nobel Prize, even if there's a minimal amount of physics involved, qualifies for a Nobel Prize, if the impact on society at large becomes the dominant consideration. And throughout the rest of the 20th century, the next 100 years or so, the next 90 years after Marconi, there is no other example of this kind. Now, I myself was in the 80s or so, in 90s, working on heterostructure bipolar transistors and a little bit on heterostructure lasers. And I remember that around that time, some of my colleagues were wondering whether I would qualify for one of those prizes. And I never took this very seriously, which incidentally was very, very good for my mental health. My answer was, well, they don't know the rules. There are no such things as Nobel Prizes in applied physics. What I had failed to realize is that in 2000 they changed the rules. And the best example is not the prize to me and Al Ferrov, but it's the prize to Jack Kilby, who had come up with the first integrated circuit. And if you think about this, there would be no computers without integrated circuits. And in fact, our entire electronics industry wouldn't exist without integrated circuits. So here was another one of those examples of where the invention made a huge impact on society at large. And so that was it. So the question that one naturally asks, well, was that 2000 an isolated case, or was that a new idea? And I remember talking to somebody who was a member of the Academy, and he agreed with me that this was something different from the past. And when I asked him, well, is this a new direction, or is that an isolated case? Well, we'll find out. And now, at that point, it was very clear to me that there was one potential candidate that fall in that category of changing civilizations, changing society at large. And that was, of course, the blue LED. Because once you have the blue LED, you realize all the other things. And I don't want to repeat what Steve already has done. It was an obvious case. The only question, and it was clear to me through some indications that the Nobel Committee was actually thinking about this one. But of course, they think about a lot of things. The majority of the people about whom they're thinking do not get the prize. So the question then is, of course, well, who would get it? And there were some people, some school of thought, well, the first person who actually worked with gallium nitride and showed that it can emit light, which was Jack Pankow at RCA, should be on the list. And I never took this terribly serious because it was an isolated case. And I don't think Jack Pankow took it very seriously. I know him quite well. Then, of course, all right, it's just another LED. But you see, all the other LEDs did not have that society-influencing property. And so it was clear to me personally that if the Royal Academy would choose the blue LED, it would go to those people who had made that decisive breakthrough that made it possible to create from blue light any color of light. And this is, of course, eventually what did happen. To me personally, it was very gratifying because, in fact, sometimes think it's a second prize for myself. And not only because it involved heterostructures, but there's another reason why it was very gratifying. When I came here in 1976, I came here with a plan. I had to recommend it to the leadership here at UCSB to totally forget about silicon technology and to put all of our emphasis into the new field of compound semiconductors, because I was convinced that compound semiconductors would someday become important. And if there was a lot of doubt during many years whether this prediction was right, I think the event that we're celebrating today shows that this prediction was in fact entirely correct. Thank you very much.
And now it's my great pleasure to introduce the 2014 Nobel Prize laureate in physics, Tsuji Nakamura.
Oh, thank you. Thank you. Oh, thank you. Thank you. Thank you. Thank you. Thank you. Please thank you so much for coming here today. At first, I'd like to thank Henry, Chancellor Henry, but today he's not here, so I'd like to thank Deering. She's not Chancellor today. Thanks so much. So because since I came here, always Henry said, I'm your manager, to receive Nobel Prize in the future, something like that. So I'd like to thank Henry a lot. Also, next, I'd like to Dean Roth to organize this lecture. Thank you so much. And also, I'd like to thank Steve Denvers, Mesh Mishra, and Jim Speck, and because we worked together for the new Center of Solid-State Lighting Energy Electronic Center. So always we work together to develop gallium nitride-based devices. Thanks so much. Also, I'd like to thank Professor Herb Kromer. He invented heterostructures, and he received the Nobel Prize by invention of heterostructures in 2000. Without his invention, we cannot make any devices, any device like we cannot make LED laser diode without his invention. His invention, great. Also, Mesh Mishra is developing a power electron device. Without his invention, he cannot make his power electron devices. His heterostructure, we have to use all kinds of devices. We have to use his invention. So thank you, Professor Herb Kromer. Without him, we can't do anything. It's working. This is different. I don't know. Sorry.
It was supposed to be right here. There it is.
Okay. Okay. Thank you. Okay. So today I'd like to talk about about my invention. How could I invent blue LEDs? And so this is my title: Invention of Blue LED and Laser and Solid-State Lighting. So this is the outline of my talk. What is a LED? Just introduction. And before gallium nitride, zinc selenide-based material was very popular to develop blue LEDs. And the next is GaN on sapphire, because current blue LED is grown on sapphire substrate. And number 4 is why is in-GaN LED so efficient? Because when we grow gallium nitride on sapphire, huge number of dislocation means a huge number of crystal defect. In spite of a huge number of crystal defects, blue LED is very efficient. It's amazing. It's a miracle material. That key material is indium gallium nitride. So, and the next is impact of basically application. Impact hybrid in-GaN indium gallium nitride based LEDs. So introduction. So material is gallium nitride. So using gallium nitride, I could invent blue LEDs. But this material used for LED, also power electron devices. Here Professor Mishra make very good power electron device. Also he started his own company. Also, Steve mentioned we are expecting the next lighting should be laser-based lighting. So we expect a lot for laser lighting for near future, instead of LED lighting. Also, this material also is solar cell or the thermoelectric devices. So this material is used for all kinds of devices. So right now, the biggest market is LED. LED is already Steve mentioned. LED is for solid-state lighting and decorative lighting. Also, automobile headlamp and indoor lighting and So also agriculture, So space agriculture, they're interested in the LED lighting. And also all kind of mobile device. Mobile device have to use LED lighting because mobile device is only power supply battery. Means the battery only operation voltage 3 volt. Only LED can operate, battery. So that is the reason why LED is used for all kind of, mobile device, iPad, iPhone, all kinds of, devices. So also this shows the evolution of a man-made light. So long time ago, 15,000 BC, oil lamp. But this is the efficiency of LED, higher the better. So 0.1 lumen power. Efficiency is very poor. And 19th century, light bulb, the efficiency is only 16 lumen power. But 20th century, fluorescent lamp, efficiency is much higher, 70 lumen power. This is the efficiency, And now, 21st century, now recently, one company, American company, Korea announced a 300 lumen power using LEDs. So efficiency is much higher. You can So using LED, you can save a lot of energy. So what is the LED? So a light-emitting diode produces light of a single color by combining positive and negative charge. Negatively, we call electrons inside the crystal. So basically, this is a battery. Battery supply electrons, and the hole is a negative. Hole this one, and so electron hole recombine in the active layer, and we can observe the photon emission, light up. So these are basic structure. So basically, we need N-type layer and active layer and P-type layer. So in the case of gallium nitride, missing layer was P-type layer and active layer. So this is for nitride, So gallium nitride-based LEDs, missing layer is P-type layer and active layer. So basically, we could develop the P-type layer and the active layer. That's the reason why we received Nobel Prize this year. So very simple. Yeah. So this is also real LED. So basically, here you can see substrates. For substrate, we use sapphire substrate, sapphire. And this is thin layer is gallium nitride. N-type gallium nitride, and active layer is indium gallium nitride, and P-type GaN is here. And the size is 0.4 millimeter. It's small. So this is development of red, blue, and green LED. So in 60s, Professor Nick Horoniak of University of Illinois developed red LEDs, first time. And the efficiency of red LED increased gradually like this. Now almost 100 lumen power. But the missing color was blue and green. So since 60s, many scientists, researchers had to try to develop blue and green LED, but nobody could make it. But I could invent high efficient blue LED in 93, also green LED is 96. And now 3 primary color available. So using 3 primary color, we can make all kinds of colors, including white, any kind of color, display. So you have seen the LED TV, because LED TV needs 3 primary colors. So the reason why they can now make all kinds of TV. Also, this shows the luminous efficiency, lumen power, efficiency as a function of years. So these are conventional lighting. So conventional lighting, fluorescent lamp, halogen lamp, you can see that. So these are conventional lighting. Already technology is saturated, no more improvement, because technology, no more improvement for the technology, no more, we can't find any more technology. But this is LED lighting. You can see LED white lighting. You can exponentially increasing, because this is a semiconductor technology. We can automatically, control everything, So right now, already Cree announced the 300 lumen power, So you can see how efficient using white lighting for the, LED, for lighting. So next, backdrop. 2.6 versus 3.9 in the late 80s. So I started blue LED research in 89. So in 89, there are 2 materials to make blue LEDs, 2 materials. One is zinc selenide, and another one is gallium nitride in 89. And in the case of zinc selenide, people could use gallium arsenide substrate to make blue and green LEDs. So these are blue and green. And because in this case, lattice mismatch is almost zero, means no crystal defect using this gallium arsenide. No crystal, perfect crystal. But in the case of gallium nitride, there are no lattice match substrate. Only available substrate is sapphire. But the lattice mismatch is 16%. Means huge, when you grow gallium nitride on sapphire, huge number of dislocation, huge number of crystal defect. Number of dislocated density order of 10 to the 9th. But this one is almost a perfect crystal. So that's the reason all of people selected zinc selenide to develop blue LEDs. Only few people selected gallium nitride. Those people are crazy at that time. It's true story. I'm not joking. Crazy. So you can say this is a gallium nitride grown on sapphire. These are dislocation, crystal defect. All the number is order of 10 to the 9th. So at that time, nobody expected we can make high efficient blue. Nobody, almost zero. In 89. So this is in 89. Zinc selenide versus gallium nitride for blue LED. So zinc selenide on gallium arsenide substrate, high crystal dislocated density is less than 10 to the 3rd. And very active research. Almost 90% of the researchers worked for this one. And also gallium nitride on sapphire, poor crystal dislocated density order of 10 to the 9th. This is a number of crystal defect. Number of researchers less than 1%, Also, so there's in Japan, there's a big applied physics conference in Japan. It's called the JSAP. In 1992, I attended this conference. For zinc selenide session, number attends more than 500. More than this audience, number is more than this audience. But in the case of gallium nitride session, including session chair and speaker, less than 10, including me. I'm not joking. Small room, not this. For this session, zinc selenide session, this size of a room, but the zinc selenide, gallium nitride session, small, tiny, and so actively discussed. So gallium nitride, at that time, people say gallium nitride has no future. Gallium nitride people have to move to 2.6. This is common sense at that time. Also another thing, in 89. So in my case, in 89 I started gallium nitride research. So the reason seeking to, so in my case, why I selected gallium nitride means I wanted to get the PhD degree because my degree I received only master degree from University of Tokushima, and I went to University of Florida 1 year from 88 to 89, and I learned in the United States for science, most important is a PhD degree. If we don't have PhD degree here, only technician, no? So I learned in the United States, most important is a PhD degree. So after I came back from University of Florida in 89, my dream was to get a PhD degree. So if I select zinc selenide, there are tons of papers. So I expect I cannot publish any paper, But if I select the gallium nitride, basically no paper. So even if any result, I could write in some kind of papers, So in Japan, if we can publish at least 5 scientific papers, we could get a PhD degree. It's called paper degrees, Yeah, it's true. So my degree is paper degree, So that's the reason why I selected gallium nitride. I never expected I invented blue LED. Never thought I could invent blue LED. Just my dream was to get a PhD degree, It's true story. And also, my company was a small company, and almost a budget is almost zero. It's true. And researcher only me. So no future. So I never expected. Also, another thing is big thing is in 70s, 80s. So LED means we need dislocated density less than 10 to the 3rd. This was common sense. Common sense. It's amazing. When I attended the conference, every conference, all of scientists working how to reduce the dislocated density less than 10 to the south using gallium arsenide, indium phosphide, all kinds of semiconductors. Because in order to make LEDs, it was common sense. Dislocated density less than 10 to the south. So that's the reason all people selected zinc selenide. A lot of paper there, you can read a lot of paper. In order to make LEDs, dislocated density less than 10 to the south. All paper said it was common sense. So that's, if we select the gallium nitride, it was crazy, very crazy, So next is the story, gallium nitride takeoff. So basically, for first gallium nitride crystal grown by Dr. Maruska of GE at that time. So he made the first gallium nitride crystal. So he did a great job. I expected he could get a Nobel Prize, but I don't know why. He did a great job, And also he made the first blue LEDs. This is the first blue LEDs, and in 73. And but he couldn't make P-type gallium nitride. Just instead of P-type gallium nitride, he used insulating layer, semi-insulating layer. So we call MIS, mistype LED, no P-type, N-type and insulating layer. And the metal contact, we call metal insulator semiconductor, miss LED. But anyway, this is LED too. And so in Japan, 86, this is another Nobel laureate, Professor Amano and Akasaki. They made, they could make the very high quality gallium nitride film for the first time using aluminum nitride buffer layer. Sometimes we call nucleation layer, using aluminum buffer. So without aluminum buffer layer, surface is very rough and there are cracks on the film. There are cracks. But using aluminum layer, it's surface very smooth and mirror-like and no crack. So also another breakthrough is Professor Amano and Akasaki in 1989. They could make first P-type gallium nitride using electron beam irradiation treatment. Low energy electron beam treatment. And so this is a P-type, this is P-type, but the Hall constant is very small, but the resistance is very high. But they could show the beautiful LI curve. So this is like a real PN junction diode. But they couldn't observe the electroluminescence because it's very, very dim. This is gallium nitride. Because, I told you, if gallium nitride grown on sapphire, huge number of dislocation, order of 10 to the 9th. In that case, no emission, basically. But they got Nobel. So their research is up to here, no more. But they got Nobel Prize because they demonstrate first, P-type layer, also first layer. So next is so in 89, since 89, so before their invention of P-type gallium nitride, so almost 1 year ago, I started gallium nitride research. And so in my life, this is the most important breakthrough for me because I started nitride blue LED research at the beginning of 89. And initially, I purchased a commercially available MOCVD. This is MOCVD, the crystal growth reactor. We can grow gallium nitride using this MOCVD. It's just a reactor, no? And initially, I purchased a commercially available MOCVD. It cost $2 million US, $2 million. It's very expensive. And I tried to grow gallium nitride, but no growth. Even if there are growth, color is black. If, good gallium nitride crystal means the color should be transparent, but black. And so several months I worked for the commercial-based MOCVD, but no result. So after several months later, I made a decision. I have to modify this MOCVD. So why I started the modification, and almost I had to spend almost 1.5 years to modify the commercial-based MOCVD. At that time, it's crazy. In the morning, every morning, I modify the reactor, and every afternoon, I did a growth, almost 4 rounds or 5 rounds. Every day, I did this pattern, same pattern. In the morning, I have to modify the reactor, and afternoon, I have to do the growth. I continued almost 1.5 years, and finally, I could develop this 2-flow MOCVD. And I did the gallium nitride growth without buffer layer. And I measured the whole mobility, and the mobility was best in the world. Best means the world, means better than, higher than the Professor Akasaki Amara's gallium nitride, you know. So that it happened in 91. And the next, I tried to grow buffer layer. So Professor Akasaki and Amaro use aluminum nitride buffer. So I work for a company, you know, I have to care about the IP, no patent. So I have to use different technology. So I use the gallium nitride buffer layer, and I obtain the very high crystal quality, and the mobility is, highest ever reported. So it means the crystal is the best, you know. So I could publish a paper, you know. And the next is P-type gallium nitride. So Professor Akasaki and Amaro developed the P-type gallium nitride using electron beam. But in my case, just I used thermal annealing. You know, initially high resistivity, but just using the thermal annealing, ambient gas should be nitrogen. Now, using nitrogen ambient thermal annealing, I got the P-type gallium nitride. Initially high resistivity, but using just thermal annealing, it became P-type. So, and also I did another experiment. So initially P-type gallium nitride, and this is annealed using ammonia ambient gas. And in that case, resistivity becomes semi-insulating. And this sample is annealed using by changing nitrogen ambient. This one became low resistivity. So just changing the ambient gas, this resistivity is reversible. From this is ammonia ambient gas, nitrogen ambient, this is reversible. So I guess something is into the crystal or outside the crystal. And also I guess atomic hydrogen is related to this phenomena. So I found the hydrogen is atomic hydrogen passivated magnesium acceptor. So I proved the hydrogen passivation is called the whole basin mechanism. So because this is a big mystery, because Maruska started the gallium nitride crystal, in '69. Since '69, nobody could understand why people could not P-type gallium nitride for 21 years, almost 21 years. No? But I could clarify the origin of the whole composition mechanism using hydrogen passivation. So, so this is this is Professor Chris Panderos. He's also professor here at UCSB. His paper. So he also theoretically, clarified hydrogen, hydrogen passivated magnesium. So this is another big breakthrough. Also another, for me, biggest breakthrough is indium gallium nitride layer. Because this is a key material, I told you. So when you grow gallium nitride, huge number of dislocated density. Only this indium gallium nitride shows a strong emission in spite of huge number of dislocation. But nobody could grow indium gallium nitride until I could grow high quality indium gallium nitride. So in '92, I could grow fast, high quality indium gallium nitride, which shows a strong blue and this is blue and violet emission, also green emission. So, this is most important. And so indium gallium nitride can be used for emitting layer. So indium gallium nitride is sandwiched by P-type gallium nitride and N-type gallium nitride. But in this case, aluminum gallium nitride, but it's the same as the gallium nitride. So it's called the double heterostructure. Double heterostructure. And double heterostructure, Professor have chromas invention. No? We have to always use double heterostructure. So using these double structures, deep structure is possible only using indium gallium nitride and gallium nitride, So the indium nitride is key, and out power is 2.5 meters. This is high brightness LED. So Steve mentioned in 94, I demonstrated this blue LED at a conference, and Steve said, "Oh, it's something, Yeah. So this is the Nobel Prize Foundation citation of our invention. So they copied my paper. This is what's it? Zinc doped ingot and then N-type argon P-type. So this structure they copied this one. And so, yeah, hole. And my invention is I told you P-type layer, active layer, and, So the reason why, I told you, only among nitride-based material, only indium gallium nitride shows a very strong emission in spite of huge number of dislocation. Still, we don't know exact reason. But one possible explanation is done by Professor Chichibu. And his idea is there's a localized states in the indium gallium nitride layer, localized state like this. And so electron and holes is injected into the emitting layer, and those electrons and holes laterally recovering at these localized states before they are captured to non-radiological center caused by crystal defect, means dislocation. So this is dislocation, no? But the injected carrier cannot reach dislocation because they easily capture to these localized states. So the idea is indium gallium nitride in the indium gallium nitride, there are lot of huge number of localized states caused by, in this case we say phase separation, but still we don't know exact reason. But anyway, most possible explanation is there are lot of localized states in the indium gallium nitride area. So you can see this is normalized emission efficiency as a function of dislocation, number of crystal defects. When you grow gallium nitride on sapphire, dislocation is 10 to the 9. You can see only indium gallium shows the strong emission, strong efficiency, high efficiency. Other material, gallium nitride, no emission. Other compounds, no emission. I told you. So this is in 70s, 80s, common sense. Because if there are huge number of no emission. But when we use indium gallium nitride as emitting layer, intensity is very high. So that is the reason why luckily we could invent blue LEDs. And also, initial LED we didn't use a quantum wear, but in '95 we made a quantum wear blue, green, yellow LEDs. So this, this is now a basic structure for all of commercially available LEDs. They use a quantum wear active layer, and And also we could develop the first demo, develop violet laser diode. So this is a laser diode, this is blue laser diode. So basically, in '96, we could develop first laser diode. Key is indium gallium nitride multi-quantum wave for active layer, So these are history, So you can see, basically, Professor Akasaki Amano developed high quality gallium using an aluminum buffer. And in '89, they developed the first p-timer using low energy electron beam. Their result only this one, and they got Nobel Prize. So fast, what I want to say that for fast is the most important. Fast time. They need a fast time. And in my case, I started gallium nitride researching at the beginning of '89, and I got to the first crystal using buffer layer, gallium nitride buffer. So everybody uses gallium nitride buffer because crystal better than aluminum nitride buffer, But later than their result, fast is most important, And next, p-type gallium, I got the p-type using submarine. All of companies use submarine to obtain p-type gallium. But later than their invention, nobody uses low energy electron beam radiation, but fast is very important to get a Nobel Prize, Also, I made ingot layer. This is the first time, ingot makers, Nobody could make the ingot. This is a key material, to make all kind of emitting device. This is a key, And so we could develop all kinds of devices, blue LED, violet laser diodes, CW, green, and white. So because we could invent a fast ingot layer. Ingot is a key material. So this is another contribution to our high-efficient LEDs. So you can see substrate sapphire. This is sapphire substrate, and the buffer layer. So Akasayama developed aluminum buffer 85. I make it gallium buffer, but later than the and p-type gallium they use electron beam 89. But in my case, just submarine, and I clarified the hydrogen participation as as a whole compression mechanism. But the most important finding in our case is just the indium emitting layer, because without this layer, nobody can make any emitting devices. This is the key, because interface, there's a huge number of dislocation, because gallium nitride is lattice mismatch with sapphire, because a huge number of dislocation is the order of 10 to the 9th. Without the ingot layer, no emission, indium layer, no emission. So indium layer is a key material. And so initially, I told you, this is a published scientific paper, PIA. So, before 95, zinc cyanide paper was much larger than gallium nitride, but now gallium nitride paper is much larger now. So impact, a bright future with gallium nitride LEDs. So energy consumption, significantly reduce electricity need worldwide. So this is California. The electricity consumption in California by end use for, So how electricity consumed in California, basically lighting consume 35% of electricity consumption in California, 35%. And so this is the latest DOE report. You can say, DOE studied the effect of the LED. So 46% electricity saving in 2030, using LEDs. And the saving is 250 billion US dollars from 2010 to 2030 alone. This is only in the United States. It's a huge, you can say, huge energy reduction, And next is solar-powered LED lighting. So you can see third countries basically no electricity. You can see this region is 75% no electricity, and this region also no electricity. So 1 in 5 people on the planet live without electricity generally because they are not connected to the grid, poverty and politics. Both can influence the way countries shape their grid infrastructure. So basically no electricity means no lighting. And so they have to use kerosene lamp, kerosene. 2 billion people rely on fire, kerosene candles for indoor lighting. It costs a lot because they have to spend 1/4 of their salary on lighting alone. Also, kerosene causes a fire, very dangerous. 2.5 million people, in India along suffer severe burns due to fire because kerosene will cause fire. It's very dangerous, you can say. Also, health hazard because they have the carbon and the carbon dioxide. They have, respiratory disease. So you can say this is a testing of the kerosene lamp. You can say in 5 minutes this becomes black due to carbon. It's not good for health, Also fire problem. But now using solar cell plus battery plus white LEDs. White LEDs can be operated battery. I told you operating voltage only 3 volts. And the battery is charged by solar cell daytime. And nighttime, battery can operate white LEDs because only 3 volts required. So this is basically mobile lighting, mobile lighting. So bringing off-grid lighting to the developing world, LED cost. Also cost is very cheap because solar cell plus battery plus white LED, I don't know how much, for John Barno, $10? I don't know. How much now? $10. Yeah, around $10. So $10. So by just invest in $10, system solar cell plus battery and white is lifetime is at least 2 or 3 years without any maintenance. It's very cheap, but kerosene you have to buy every month. You have to buy kerosene now, so it's very cheap. Payback is only just 6 months. LED costs less than kerosene on an annual basis, and the payback is just 6 months. Allows education also at night. So using this LED lamp, they can study, In the few months, we have had the white LED lamps. The improvement in the children's academic performance has been absolutely remarkable, Headmaster Barak, And this is an NPO of United to Light, supported by John Bauer, So, this does NPO, this, eliminate the kerosene lighting along with its health, safety, and carbon dioxide problem. high-risk compact light source with solar cell. So basically, here there is a battery inside, and this is a solar cell. So daytime, this solar cell charges the battery, and the nighttime, this battery, operates the LEDs. So clean energy, no kerosene, no fire, no health problem. And the lifetime is at least 2 or 3 years. Just the investment $10, and no maintenance for 2 or 3 years. It's clean energy. So this is very popular for third countries because very cheap and very safe. They can understand, Also, LED save lives too. So day after Nobel announcement, ferry sink at night in Taiwan. Taiwan, ferry sank at night. And life-based equipped is LED. So this LEDs, life jacket equipped LEDs, and this nighttime. So this life jacket always emits the light using LEDs. So nighttime, easily rescue team could point to who was there. Everybody swimming on the sea, But the nighttime, without LED, nobody can find who is over there, But luckily, all the jacket has a LED. They turned on, and easily they could find where the people there. So rescue team 43 lives, as LED helped to rescue, So Chancellor Henry came to me, when I got a Nobel Prize. Do you know this news? In Taiwan, coincidentally, LED helped a lot of people, And I'm so excited about this news, Yeah. So this is a member of the solid-state lighting energy center, and we are working for the next generation solid-state lighting. Especially, we are right now focusing on next generation laser lighting, because right now LED lighting, but we expect laser lighting is next generation lighting. So all of here people are working on next generation lighting. Also, Mesh group is working on power electron device. Also, paradigm is gradually become popular. Using gallium nitride-based paradigm, we can save a lot of energy, almost same as LEDs. So, okay. That's all. Thank you so much.
So we have some time for a couple of questions. There's microphones up at the front. Please come to the front and if you have a question.
First, congratulations. When you were working on this, or the passion to actually carry on and invent from 1989 on, did you really realize the impact you were going to have on energy and health and so forth? Was that in the back of your mind that this was going to have such a big impact on society?
No, I never expected, because at the time, only available color was only red for LED, red color. And just I wanted to invent the blue and the green LEDs. That's it. Because blue and green are available, I expect we can make any kind of colors. And also we can make LED TV, full color, something like that. So I never expected the efficiency of blue LED become very high like this, Because so I never expected this huge market, huge, Because I never expected that, because the efficiency becomes so high, because I told you, defect density is, 10 to the 9th. 10 to the 9th, When I made the first PN junction LEDs, PN junction, gallium nitride, P-type, and P-type gallium nitride, N-type gallium, just PN junction, no indium gallium nitride. And I operated the LEDs, but very, very, tiny emission. But I worry about the lifetime, because distribution density 10 to the 9. 10 to the 9, the lifetime is very short. Immediately die, LED should be die. And I tested reliability tested, lifetime testing. And I started lifetime testing today. And the next day I came to my office. I checked the LEDs. Still LED surviving. That is amazing. That was 92. So basically I never expected. But after invention of indium gallium nitride, suddenly efficiency increased. That happened in 92, 93. 93, I say, oh, there are some huge market because it's so bright, Yeah. So basically, gradually. Yeah.
Any other questions? If not, Suji, thank you very much.
Thank you so much. Thank you.